Carbon, the shape of life. Here you see something that kind of looks like the skeleton, the outline of a soccer ball. It's not perfectly round, it's made out of little panels that are either pentagons or hexagons, but it approximates a round shape. In the same way, if you were to look at, say, the fingers of your hand looks like to be a relatively complex and smooth shape, but it's actually made of little parts that are more simple, just like a soccer ball is actually made out of simpler figures. In the same way, we're going to try to show you how carbon forms a whole bunch of different shapes that are relatively simple, and yet somehow all these simple shapes based upon carbon can be arranged to form an almost inexhaustible number of complex shapes. Carbon really is the shape of life. So let's consider the following shapes. We can have rectangular solids like cubes, or we can have cylindrical tubes like a straw, or we can have a chain that forms an even numbered ring like a hexagon, or we could have an odd number of rings like a pentagon. We could take a chain and wind it up in a spiral shape like a spring or a coil. Or we could take the same chains and pull them tight like you were holding a sheet and stretching it tight. These shapes, as well as many others, can be produced by molecules based on carbon. I want to give you some examples of these simple shapes at work in the real world. For example, we can take these chains and we can make hollow tubes, little cylinders. We call them nanotubes, which just means tiny tubes. And in fact, these tiny tubes can be used to build circuits and machines. Here in the animation, each dot represents an individual carbon atom, and the lines connecting them represent bonds. And you can see how a series of carbon atoms can be arranged in a sheet that rolls over and folds upon itself and forms a hollow tube. If you've ever wondered about carbon fiber, this is kind of what carbon fiber looks like at the molecular level. You have fibers that are made like this, and they are an active area of investigation by chemists all over the world. There's a big, gigantic research program involving tens of thousands of scientists from all kinds of different places and countries and languages, and they're all collaborating in a branch of chemistry called material science, and many of them are working on applications of carbon fibers. And it's hoped that perhaps eventually these individual nanotubes can be used to build molecular-sized circuits, molecular-sized machines. If you take chains like that, and instead of coiling them up and you polarize them, that means one side is kind of positive, the other side is negative, many of these molecules will automatically form double-sided layers, which are the basis of cell membranes. In biology, you might have recognized these membranes before. You might have seen these molecules before. How you have one side with the heads pointing out and another side with the heads pointing in. The heads are attracted to water, and there's water just outside the cell, and there's water inside the cell membrane, and so they tend to automatically form these layers, kind of like a highly organized soap bubble. Now, instead of talking about a liquid, like the contents of a cell, if we talk about a solid, if we take carbon and we arrange it in solids, if you take just carbon atoms by themselves, they produce complex forms with unusual properties according to how their crystal lattice is organized. In this illustration, the gray spheres represent atoms of carbon. The green rods represent bonds between them. This is the molecular structure of graphite. Graphite is pure carbon, but it is a soft, smooth-flowing form of carbon. The mineral graphite looks like this, kind of shiny, like a rock. And you might think, oh, it's a rock, it's very hard. And yet if I took a piece of graphite and I ran it over a sheet of paper, it would produce marks just like a pencil. And that's because a pencil doesn't have lead inside it. We sometimes call it a lead because it looks like lead, but it's actually this soft, smooth, flowing form of carbon. Why is it soft? Why is the pencil lead soft? Because most of the carbon atoms are not hooked up to every other carbon atom. They're only bonded to a few atoms in a single sheet. And so when you press down with your pencil, you're pushing one little sheet of carbon atoms off at a time. And it flows out quickly and smoothly. But now let's take these same exact atoms of carbon, which when arranged like this are soft and smooth flowing. Let's rearrange them like this. This is a super strong molecular structure. You can see how every gray sphere is hooked up to every other gray sphere. There are many more of the green rods representing chemical bonds, and this is diamond. Diamond is the hardest naturally occurring substance on Earth, and a girl's best friend. When we think about diamond, we often think about beautiful gemstones like this, which are very valuable because they're relatively rare. Most diamonds aren't very large. Most diamonds are small, like grains of sand. And in fact, most of the diamonds that are sold on planet Earth, most of the value from mining diamonds doesn't come from jewelry. Most of it comes from what are called industrial diamonds. And these are little fragments of diamond which are too small to be useful for jewelry, but they're still very, very hard. And so they are used to produce power tools. Power tools will be coated with a thin layer of ceramic, a little bit of grit. It's kind of like sandpaper, except instead of little pieces of sand, it's little pieces of industrial diamonds bond to the power tool. And that makes them very, very hard. When you talk about things like oil drilling. Now, in addition to graphite and diamond, we also have this form of carbon. This is also made of pure carbon. These were only discovered about 30 years ago. The people who discovered them won Nobel Prizes. They are little molecular-sized geodesic domes. They're made of 60 or more carbon atoms. They're sometimes called fullerenes, or more prosaically, buckyballs, and they're named after the American architect Buckminster Fuller, who liked to use these structures in his innovative buildings. Why did he like to use this particular kind of geometry? Because it's hollow, it's very large, and yet it's also very lightweight and super strong. And so these are another area of active investigation in materials science. This is another thing that chemists worldwide are working on, attempting to build molecular size machines. Now, if we take our chains of carbon atoms and we fold them up, we can make rings. We can make what are called cyclic structures. The compounds that we call sugars are in fact just rings of 6 carbons with a few oxygens and hydrogens connected to them. In the illustration, you can see how it's possible to label every carbon, hydrogen, and oxygen atom in a sugar. You can also, if you want to, draw it out. But in practice, and this is a very important fact for you to know, in practice, it's often a lot easier just to draw a simple geometric shape. So here, if you see a hexagon, that usually represents a sugar. You're just expected to know that each corner of the hexagon represents a carbon atom and that other things will be hooked to it. If we have 6 carbon chains like hexagons, we also have 5 carbon chains like pentagons. It turns out that both DNA and RNA, which are the molecules implicated in biology that carry genetic information, these all have little sugars, 5 carbon sugars as part of the structure. And you can see that here in the illustration. The gray shapes represent those sugars, and there's one of those sugars at each step in the strand of these nucleic acids. So here we have the same 6 carbon glucose sugars we mentioned before. In this case, they've been chained up. So the individual sugars are a chain of 6 carbons and other atoms, and they've been bent into a ring shape. And now each one of those sugars has been hooked together in another chain. So here we have kind of a chain of chains, and this is called cellulose. In the illustration, every one of the pink hexagons represents a separate sugar, and you can see that they form straight chains. And these straight chains can be packed nice and tightly with a lot of strength. They kind of work like bricks. The outer bark of trees is made mostly of cellulose, and this is part of the strength of tree bark, that it is made of these straight chains. Why did the chains stay straight? Well, it's because their bonds are pulling in alternating directions. It's a beta sheet, and you can see that every other bond is pointed in an alternating direction, and that is like a tug of war. When you have a tug of war, you have two parties pulling on opposite sides, and the rope gets very straight, maybe for a few seconds, maybe for longer. Why does it get very straight? Because forces are pulling in the opposite direction. So the same thing is true for cellulose. It's a chain of chains, and each step in the chain is a sugar, but each bond holding them together is moving in the alternating direction, left, right, up, down, however you want to think about it, and so the chain stays straight. And that gives it a lot of structural integrity, a lot of strength. But if we take the exact same sugar, the exact same glucose sugars, we can chain them up a different way. And if we chain them up so that all the carbon bonds are moving in the same direction, the entire chain tries to move in the same direction. It tries to rotate in the same direction. So here again you see the pink hexagons, but they're no longer straight. They are rotating in a coil. This is an alpha helix. And why do they rotate in a coil like this? Because every bond is moving in the same direction. Now, if that coiling shape seems familiar, it's because DNA has not one but two of these alpha helix coils. They are all moving in the same direction, and they will hook up the two coils. They will have information stored in the steps in between the two coils that hold it together. And to read the information, you open part of the coil and read it on the inside, and then when you're done, you close it up. And so this is called the double helix, and a double helix is made of a pair of coils just like this. Now at this point, having given you a lot of examples, it's not so important that you memorize all these examples. The important thing is that you understand that I'm giving you real-world examples of how carbon forms basic simple shapes, and how living things especially use those simple shapes to construct more complex shapes. And it turns out that carbon can form the basis of more simple shapes, more so than almost any other element. There's only one other element in the universe that even possibly could make as many shapes as carbon. But for reasons that I hope will become clear, we think if there's life elsewhere in the universe, it's probably not based upon that element. It's probably based upon carbon. And the question is, why? I really think that this is one of the most fundamental questions that I ever get asked. Students ask me a version of this question all the time. The version that students ask me is, Mr. Hatfield, do you think there's life elsewhere in the universe? Do you think there's, aliens, extraterrestrial life? And I always answer that the same way. I always tell them that there is no evidence that there is any life anywhere else in the universe. No one has provided any really convincing evidence to that effect. But nevertheless, the vast majority of scientists, including me, believe it is likely that there's life elsewhere in the universe. And then I tell them, with a mysterious smile, in fact, I not only believe that's true, but I believe that there's life elsewhere in the universe that is based on a particular element, which is carbon. Now, I actually think that's something that everyone is really interested in. They would like to know, is life likely to happen? And if so, why? And if life is likely to happen, what causes it to be likely to happen? It's not a fundamental part of the rules, and we're interested in it naturally because it determines whether we're here or not. So that might sound a little philosophical, but it is an interesting question. And you know what? Most adults know that life is based upon carbon because they've heard that over and over again. And yet, almost none of them can explain why. So I want you to be part of that small percentage of human beings that not only knows that life is based upon carbon, but you have an idea why. Understand why, we really have to understand carbon's atomic structure. So we're going to end up reviewing some information to make sure that we understand it very thoroughly.
Okay, so now we're coming to the part of the lesson where I'm just going to start reminding you of things that I've taught before. And this right here represents a box in the periodic table. And I'm going to take the simplest element, the easiest element, and that is hydrogen, whose symbol is capital H, right? And if we look at the periodic table, we'll find that's the first box, and we'll also see that above the symbol for hydrogen, there's a number. And it's the number 1. Hydrogen is element number 1. Why is it element number 1? Because it's got 1 proton. The number in the periodic table tells us the number of positively charged protons that appear in the nucleus. Now, I'm going to need to keep track of protons, so I'm going to go ahead and I'm going to have a symbol for the proton, because I don't want to keep having to write out the word proton. That's too hard. So I'm just going to have a symbol for the proton, and that symbol is going to be a big red plus sign. It's going to be a big red plus sign because protons are positively charged, and it's going to be red because, and I can't make this up, if you get a proton really energetic, excited, moving very fast, it will glow. And the color it glows is a pinkish red color. So that's what that keeps track of. In regular chemistry, in most of the year, we didn't bother keeping track of the neutrons. We just knew that they were there. We sometimes worried about where the electrons were, but the only electrons we really worried about the most, we worried about how many electrons were on the outside, because that's where regular chemistry takes place. And we're still going to worry about that. But what I want to do now is I want to use what we just did in the last lesson, which is the nuclear notation. In the nuclear notation, we use the symbol of the element, and we put 2 numbers in front of that symbol. Instead of keeping the numbers inside of a box, we take the numbers out. So our general form is that we'll use some symbol for the element, and then we'll have an A number and a Z number. Now, the Z number that's on the bottom in front of the symbol is always going to be the same thing as the atomic number. So if we were doing this notation for hydrogen, the Z number is the same as the atomic number, so I would just write 1 down here. Now, if the Z number is the number of protons, the atomic number, what is the A number? The A number is the protons and the neutrons together. These are both found in the nucleus, and so the A number keeps track of how many total particles are in the nucleus. Now, in this case, and this is a little weird, hydrogen has 1 proton, but it doesn't need a neutron. So in the simplest version of hydrogen, it doesn't have a neutron. It can have a neutron, but it doesn't need it. So in the simplest version, the only thing that's in here is the proton, and so the A number is also 1. So this is the symbol for a version of hydrogen, which is called hydrogen 1. What I want to do is I want to be able to draw this, and I want to keep track of all the basic particles. Now, for an electron, I'm going to use the symbol E minus, because this is the symbol scientists use all the time for the word electron. So that's going to be our symbol. It's got a minus because electrons are negatively charged. And it is green because if you get electrons moving really, really fast, they glow. What color do they glow? They glow this greenish color. Now, in between, the neutrons are also in the nucleus, but they are not positive, they are not negative, they are neutral. They don't affect the charge. And so we say that they have 0 charge, and so we're going to use a 0 to represent the neutrons. Okay, so those are our symbols, and we're getting ready to draw. We have to just have one more rule. The protons and neutrons are going to be in the nucleus, and we're going to figure that out from the nuclear notation. The electrons will be on the outer shell. We draw them second. We draw the inside first, and then we'll draw the outside second. And so we have to know where the electrons could go. And the rule is that they will be on shells. And the first shell can hold a maximum of 2 electrons. And the second and third shells can hold 8. Okay, so again, hydrogen has 1 proton. It's going to have 0 neutrons, and it will end up having 1 electron to balance it, to balance out the charges. The hydrogen itself is in the nucleus. So I'll make a big plus sign. And I'm going to make a little circle around the big plus sign to represent the nucleus. I don't need a neutron. There's only 1 atomic mass unit in here. And so to balance this, to complete it, the only thing I need to add is a single electron. And to do that, I'll just, I'll put an E minus here to represent the 1 electron. But since there's actually room for 2 on the first shell, I'll also do this using a different color. I'll make a little circle, and that represents an empty space that's present. Okay, so this would be a drawing for the simplest atom, hydrogen 1. Now I'm going to use one of those nuclear reaction equations. Let's say that this hydrogen is just minding its own business, floating in space, and it happens to run into a neutron. The symbol for the neutron is lowercase n. Now the neutron has a mass. So if a neutron sticks in the nucleus, if it's added to the nucleus, it will add 1 to the A number. But a neutron is not a proton, and the Z number only counts the number of protons. So adding a neutron adds nothing to Z, right? So it will add 1 to A, but nothing to Z. So let's say that happens. Let's say that a neutron collides in such a way that it sticks in the nucleus. If that happens, there are now 2 atomic mass units, and we complete the equation. 1 plus 1 here on the top is 2. 1 plus 0 on the bottom is 1. And since there's only 1 proton, this is still hydrogen. Anything that has just 1 proton is still hydrogen. This is a different form of hydrogen, though. This is hydrogen 2. Now, last week I taught you that nuclear reactions, fission and fusion, occur in the sun. Some of the nuclear reactions that we learned about, they occur on planet Earth all the time because there's enough energy on planet Earth to make those reactions go. But there are other reactions that the conditions aren't so favorable for. There's not enough energy on planet Earth to make those reactions likely to happen. Let's say that we have 2 of these extra heavy hydrogens. Let's say they run into each other really, really hard. If that happens, they could fuse together. This would be nuclear fusion. We could predict the products of the reaction. 2 plus 2 is 4. 1 plus 1 is 2. That means we're going to have a total of 4 particles in the nucleus, and we're going to have two of them are going to be protons. Now, if 2 of them are going to be protons, I need to add another X, another plus sign. And since I'm going to have a total of 4 atomic mass units, I need 2 protons and 2 neutrons, so I'm going to add another neutron. If we do this, then we're going to need another electron to balance the 2 positive charges, and so now we go to this empty space, and we put that other electron in there. And you know what? Since there's 2 protons, this isn't hydrogen anymore. This is the next element. What is the next element? Not hydrogen. If you have atomic number of 1, you're hydrogen. If you have atomic number of 2, you're helium. Now we're going to keep going. Instead of helium, I would like to draw a particular version of the next element, which is called lithium. All right. So lithium's atomic number in the periodic table is 3. And what I want to do is I want to make lithium 7. If we're going to have lithium 7, we would write it like this. The symbol of the element in front, and then the 3 on the bottom, because every lithium atom has 3 protons. And then on the top, since I want lithium 7, I'm going to write it like that. Now that means that I have 7 total masses in the nucleus. 3 of them are protons. So I'm going to need to add another plus sign. Now what about the rest? Well, there's 7 total mass units in here. 3 of them are protons. 7 minus 3 is 4. So I've already got 2 neutrons. I need 4 neutrons. So 1, 2, 3, 4. And since we have a total of 3 positive charges, I need another electron. But I can't put any more electrons on that first shell. I'm going to need to add another shell. And then on that shell, I will put a sole electron. And I'm almost done. There's one more thing I need to do. Since I only need to put 1 electron here to balance it, but since there's room for 8 electrons on the outer shell of lithium, then I need to have 1, 2, 3, 4, 5, 6, 7 empty spaces. 1, 2, 3, 4, 5, 6, 7. And so the circles you see represent those empty spaces.
And so we've looked at the hydrogen, helium, and lithium. Now you see carbon's atomic structure. And I'm not going to fill in all the blanks and answer the question that I've posed to you, but I have given you some tools to practice drawing atoms, which gives you an ability to think about their structure in a more detailed way. And here you see an illustration that kind of looks like the pictures we've been drawing. Instead of plus signs, we've got blue spheres with a plus, a little green sphere with a minus, and a red sphere, no label for the neutron. You can't see all the protons and neutrons because they've tried to draw them kind of three-dimensionally, and so they partially obscure one another, but you can see from the label that it tells you 6 protons and 6 neutrons. You can see that there are 2 electrons in the first shell, which is full, and you can see that the second shell is not full, and that it has 4 electrons, but that it also has 1, 2, 3, 4 empty spaces, because there's room for 8, but only 4 of them are occupied. And so that right there is a very powerful clue as to what happens next. Okay.